This is the wave nature of light, also known as diffraction. And just for reference, this is 13.5 in your Physics 30. 13.5 Physics 30.
Diffraction of light. A ray of light bends slightly as it passes around the edge of an object. The phenomenon of bending of light from its straight line path around the corners of an obstacle or slit is known as diffraction. Diffracted light can produce fringes of light, dark or colored bands. Drag the slider to observe how the quality of diffraction changes with the change in the size of the slit. We observe that the process of diffraction becomes much pronounced when the dimensions of the slit are comparable to the wavelength of light. Optical effects due to atmospheric diffraction of light. An optical effect that results from the diffraction of light is the silver lining sometimes found around the edges of clouds. Coronas surrounding the sun or moon are also caused due to diffraction. The illustration shows how light from the sun is bent around small droplets in the cloud. At times, diffraction of sunlight in clouds produces a multitude of colors. This optical effect is called cloud iridescence.
So diffraction is just kind of that spreading out of a wave as it passes through a small opening or obstacle. If you take a look in the first slide here, or the first picture here, we've got a wavelength that comes here, and you see it bend just slightly around the edges. As the slits get narrower, the effect is much more pronounced, and when the wavelength and the slit are comparable, you see almost a complete circle. Right? Now this occurs when light passes through a small opening comparable to the size of the wavelength. In other words, in an otherwise opaque obstacle, right? So here nothing can come through, and this opening is comparable to the wavelength. It resembles that pattern. Now, what happens if we have two of those in that come together, right? What happens is the two waves, we see an interference pattern. Two waves with equal amplitudes will overlap in phase where crest meets crest or trough meets trough, and that's where we'll see constructive interference. Or they can overlap out of phase and we wind up with destructive interference. So if we see a crest and a crest, if they were to come over together, you would get a supercrest. But if you'd have a crest and a trough coming together, you'd get nothing. Right? Look something like that. Sometimes these are called in phase or anti-phase. In phase is where crest meets crest and trough meets trough. Anti-phase where trough meets crest and crest meets trough. So here, with two water waves, we see kind of an interesting image happen here. This fellow here, and you can't see the other ball, it's just behind his head, but he's just tapping the water with two waves. And what you'll notice is that you see areas of constructive interference and areas of destructive interference. So this is constructive, this is destructive. Constructive, destructive again. Right? A couple of other pictures showing that same effect, where again you see constructive interference and destructive interference. Constructive interference, destructive interference.
Young's double slit experiment. Interference in light waves from two sources was first demonstrated by Thomas Young in 1801. A schematic diagram of the experimental setup is shown here. Light was made to pass through a slit, SO. The waves emerging from this slit was made to pass through two parallel slits, S1 and S2. These two slits served as a pair of coherent light sources because waves emerging from them originate from the same wave front and therefore maintain a constant phase relationship. Thomas Young observed that the light from S1 and S2 produced on the viewing screen a visible pattern of bright and dark parallel bands called fringes. What causes bright and dark fringes? A bright fringe appears if the light emerging from S1 and S2 interfere constructively, and a dark fringe appears if the light from the two slits combine destructively at any location on the screen.
So Young's double slit experiment, light incident onto an obstacle which contains two very small slits, a distance d apart. So this is the distance apart. When the wavelengths emanating from the slits constructively interfere behind that obstacle. Right, so we've got that wave front, continual waves coming from one point. Here we see constructive interference where the wave fronts overlapped. What we're doing here is we're really just showing the crests, so we can see where crests meet up. And thus you get these bright and dark spots. Bright spots, dark spots, bright spots. So taking a look through a laser, we've got this one beam of laser light coming through a grating, and we see all these sorts of beams of light coming from that, where we see the constructive interference. Now, the diffraction grating is really just a piece of glass with lots of closely separated lines. Again, these need to be comparable to the wavelength of light in order to actually witness this, right? And so this, for light, would actually have to be quite a small distance apart. They're used in spectrometers to split light up into its different spectra. It will look something like that, where you see all the different colors of the light coming through here. So there's a couple of formulas associated with this. The first one is d sine theta n over lambda. I believe your formula sheet, though, has sine theta is equal to n wavelength over d, right? Where d is the spacing between the lines in meters. Theta is that angle of diffraction. N is the order number. We'll talk about that here in a moment. And the lambda wavelength is the wavelength of light in meters. Oh, it's actually probably like this on your formula sheets. So what do we mean by order? Well, if we're talking about this very center one from the light coming in, we call this n is equal to 0, right? There's no angle The first bright spot we see on either side, coming from that what we call the central node, is the first order. And no, not like Star Wars, it's n is equal to 1. The second bright spot we see is the second order, or n is equal to 2, and so on and so forth. Now you'll notice here that the central maximum, where n is equal to 0, is where you're going to see the most intensity. They're going to be less bright at n equals 1, even less bright at n equals 2, and so on. Eventually you're going to run out of bright spots because your angle can't get past 90. Now, a lot of times diffraction gratings are actually not written in how much space is between each line, but in how many lines per meter. But really, all you need to do is actually do the inverse of that, right? So if I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines per meter, if I want to know the distance between each line, really I'm just inverting that, right? So it's 1 meter over 10 lines, which gets me 0.1 meters between lines. But that's not on your formula sheet. It should be relatively intuitive, but we're not dealing usually with things like 10 lines per meter, but more like 5,000 lines per meter. Then the distance between the lines would be 1 over 5,000, or 0.0002 meters apart. Now, there is a second formula on your formula sheet. Lambda, d, and n are all the same, but x represents the distance between orders, the distance between, let's say, n is equal to 0 and n is equal to 1. And L is just the distance here between the slits and the screens, right? Now, if we take a look here, we see that if we use this variable and this variable for that angle, that is opposite, adjacent, and hypotenuse. So what we've done is we've replaced sine theta in that same formula with essentially tan theta. Now, when the angle is small, the difference between the two is not very consequential, right? Because H and A are almost the same. The sine theta is going to be more accurate, but using this formula here, instead of using the opposite over adjacent, right, is usually good enough to 3 significant digits. And usually when we're talking small, we're talking usually angles that are less than, let's say, about 10 degrees or so. So let's take a look at this example here. Calculate the angle of deviation of the second order maximum. Right, so we're looking for this angle. Second order maximum, so n is equal to 2. With the monochromatic light, 4.3 times 10 to the negative 7 meters through a diffraction grating of 2 times 10 to the 5 lines per meter. Now let's take a look at what we have there. Again, we know that this wavelength is purple, and d is actually 1 over 2 times 10 to the 5, or 0.000005. And again, we're looking for the angle. So we're using this formula. That's the one that will work. We're going to rearrange this by multiplying both sides by n and dividing both sides by d. And you're going to plug in your numbers. Remember, we're talking again the second order maximum. So sine theta is equal to 0.172, or it gets you an angle of 9.9 degrees when you inverse sine both sides. Let's take a look at another one. Light falls on a pair of slits 1.28 times 10 to the negative 5 meters apart. The distance between the bright spots is 6.11 times 10 to the negative 2 meters when the screen is 1.2 meters away from the diffraction grating. What is the frequency of light? Well, we know that the slits are 1.28 times 10 to the negative 5 meters apart. We're given that. We're given the distance between bright spots here as 6.11 times 10 to the negative 2 meters. Now we're going to call n is equal to 1. And the reason for that is n is equal to 0, n is equal to 1 here. First of all, it's going to be the smallest distance. And we know the distance between this bright spot and this bright spot is in fact 6.11 times 10 to the negative 2 meters. So again, we're going to use this formula. Now this will solve for the wavelength. We find that wavelength to be 6.5 times 10 to the negative 7 meters, which is red light. But the question didn't ask about the wavelength, it asked about the frequency. But if we remember the universal wave equation, we can manipulate that, and v is equal to the speed of light, 3 times 10 to the 8 meters per second. Wavelength is that 6.5 times 10 to the negative 7 we found. We wind up with a frequency of 4.6 times 10 to the 14 hertz. And that's still red light. So hopefully this helps. If you do have any questions, please let me know, and have a great day.